We'll now discuss how we would go about partitioning our input array. We do have several different partitioning strategies out there, but the one that we're going to be using is pretty good in practice. So the first thing we have to do is to get the pivot out of the array, because if we have it while trying to partition stuff, it gets just really messy. So what we're going to do is we're going to swap the pivot with the last element in the array. That way the first n-1 elements are the remainder of the array, and we have the pivot over to the side. Now what we'll do is we'll also have variables I and j, and they kind of represent pointers for us, where they will point to specific elements in the array. So we're going to have I start at the first element of the array, and we're going to have j start at the next to last element of the array. So they pretty much serve as the endpoints of the current array that we're sorting. Let's do an example to help illustrate this, and we'll use the same set of numbers from our earlier example. So we'll have something like this. So notice that our pivot before was 6, so we moved that to the end of the array, and we actually swapped it with the 0. So 0 and 6 swapped places. We have our I being at the first element of the array, and we have j at the next to last element of the array. So what we want to do with this partitioning is that we want all the elements that are smaller than 6 on the left side of the array, and we want all the elements that are larger than 6 on the right side of the array. Because remember, we're not creating an additional array for partitioning all these. We're still going to use the same array to do this partitioning. So the idea is move all the smaller elements to the left, move the larger elements to the right. So the way we're going to do this is, while I is to the left of j, we're going to keep moving I to the right by 1 place. And we're going to skip over the elements that are smaller than the pivot, because if it's smaller than the pivot, then it's already on the left side. And we're going to do the same thing for j. We're going to move j to the left, and we're going to skip over the elements that are larger than the pivot, because those elements are already on the right side of the array. So what this means is, when we move I over to the right, we're going to stop when we have an element that is larger than the pivot. Likewise, for j, we're going to keep moving it over to the left, and we're going to stop whenever it finds an element that is smaller than the pivot. So think about what's going to happen next. So I is currently pointing to an element that is larger than the pivot, and j is pointing at an element that is smaller than the pivot. So that's what we have here. So I is pointing to a larger element, and j is pointing to a smaller element. So what happens here is, if I is to the left of j, then we just need to swap those elements. And after we do that, then that means the element that was at j is now at I, and the element that was at I is now at j. So now those two elements are in the correct places in the array. So if we use our example from before, I would stay right where it's at, because 8 was larger than 6, so we're not going to move I anymore. And j would move over 1 place, because j was initially at 7, which is larger than 6, but then when we move it over, as we see here, it's now at 2, which is smaller than 6. So what we would do then is just swap the elements at I and j, and we would just keep repeating this until I and j cross. Once that happens, then we know that we have completed the partitioning. So let's just continue our example. So here is our array after swapping I and j. So we see that 2 is now on the left side of the array, and 8 is on the right side of the array. So now we're going to keep moving I to the right until it finds an element larger than 6. So we see that if we move it to 1, well, 1 is less than 6, so we're good. We would move I over to 4. 4 is less than 6, so we're good there. And then we move I to 9, and we see that 9 is larger than 6, so I is going to stop at 9. Then we'll move j. J will move down to 5. Well, 5 is less than 6, so j is going to stop right there. So sure enough, this is where I and j would stop after moving and trying to find elements to swap. We'll then swap the elements. So here we have swapped the I and j, so now 5 is on the left side and 9 is on the right side. So now we would simply move the I and j until they're in the correct spots. Well, at least until we find a value that's shouldn't be there. So we move I over to 0. 0 is less than 6, so we're good there. I moves over to 3. 3 is less than 6, we're good there. I moves over to 9. Well, 9 is greater than 6, so I will stop at 9. And then j will move over to 3, and 3 is less than 6, so j is going to stop right there. So this is what we would get. So this is the result of moving I over and j over. And notice that here they have crossed. So at this point, since I and j have crossed, well, we don't perform any more swapping because now we have all the smaller elements on the left side, we have all the larger elements on the right side. So what about the pivot? Well, that's the final part. So we need to swap the pivots with the element that's pointed by I. Now, why it's I is because I is currently pointing to a larger element. So we would just simply swap it. So if we go back to our example, we would swap the 6 and the 9. So our pivot was at the end of the array, and I was, well, kind of that spot right there. But we would just simply swap the 6 and the 9. Now, why does this work? Well, what we find is that after we swap the value of the pivot with whatever I was, we know that every element in a position that's less than I must be small. And this is because either each element in this area either had a small element to begin with, which means when I went to it, it just skipped it, or the value of that element was large enough where it was swapped with an element that was smaller than the pivot. So everything before I has to be smaller than the pivot. And we can use a similar argument to show that every position after I must be larger than the pivot. We'll now go back to the question about the elements that are equal to the pivot. What should we do with them? So we mentioned before that we keep moving I and j, and we stop whenever we see an element that's either greater than the pivot or less than the pivot, depending on if we're dealing with I or j. So the question we should be asking is, should I and j stop whenever we see an element that's equal to the pivot? Well, the answer to that is yes, we should. It's best to actually stop whenever we see an equal value, just to make sure that the sizes of the subarrays are somewhat even. We mentioned before that it's not a huge deal if they're off by a little bit, but if we get a case where all the elements in are one array, we could encounter a problem. So it's best to stop when we do encounter an element that is equal to the value of the pivot. Let's just suppose that we don't stop. It is possible that we can get uneven arrays. So let me give you an example just to give you an idea of what could happen. Let's say we have an array where all the elements have the exact same element. So if I and j didn't stop, that means when we move I, it's going to go all the way to the end of the array. And then for j, it would keep moving until it gets all the way to the end of the other side of the array. So what would happen is the pivot would actually swap with the next to last element. And that means everything before that element gets stored into one set. Well, it doesn't get stored, but it's designated as one set. So that means everything is technically in S1. So what that means is our running time would become O of n squared, which we've already mentioned is the worst case scenario for quicksort. So the moral of the story is, yes, stop when I or j encounter a value that's equal to the pivot. There is one more issue that we need to address for quicksort. What we find is if the array is very small, and here we're saying that the number of elements is less than or equal to 20, quicksort actually doesn't perform as well compared to something like insertion sort. And since quicksort is a recursive approach, these cases will occur quite frequently. So when we look at smaller and smaller portions of our array, we'll eventually get a portion that is less than or equal to 20. So we will encounter this quite a few times. So a very common solution is to say that whenever we get a small array, we don't use quicksort in that case. Instead, we can use another sorting algorithm that is efficient for small arrays, such as something like insertion sort. And from an execution perspective, this can save about 15% of the execution time if we use insertion sort for smaller arrays instead of quicksort. So what we would say is a good cutoff is, we'll say n is 10. Now, we could have the cutoff be anywhere between 5 and 20, and we would get similar results, but for our purposes, we're just going to say that when n is 10 or less, we'll use insertion sort instead of quicksort.